policies and just I need to explain.
I'm non-elegant.
I'm not very elegant person.
Well, 1, 2, 3, 4, 5. A little less than 50%. Again, thanks for coming. Thanks for waiting. Who we are and what we are doing. Where we are in the class. So our main goal from now on is to complete research projects. And those of you who will not be yet on the travel to Thanksgiving are welcome to join evening session, where some codes will be shared. There will be total 3 labs today, in 1 week and in 2 weeks. And the lab which is in 1 week is most important, which by the end of this lab you are expected to have all results for your projects. Okay. The course material is arranged in a way that we slowly complete general aspects and come to more practical aspects as close as possible to the projects. So this remaining handful of lectures, it will be more and more oriented to practical things. So right now we need to complete angular momentum, then make connection of angular momentum and spin, and then the remaining time will be on reactions and spectroscopy, like interaction with materials and molecules with electromagnetic wave. Where did we stop last time? Oh, okay, about the projects. Let me speak about it a little bit more. So the first part where all projects are one-dimensional potentials for propagating wave packet. First section from here to there deals with Cartesian projection of position of electron. The second part deals with Cartesian direction coordinate, where our one-dimensional x dimension is interatomic distance or something related to interatomic distance or coordinate. So for everyone who didn't decline to do the chapter 1, all supplementary information, codes, and input files are ready. They were covered in previous labs and codes were distributed. So just run and complete. If you didn't install MATLAB on your laptops, I've shared a little video that a student working in my group put together, so you can watch it, but maybe most of you already have it. So this is kind of done. For the rest of projects here, the design of the potentials is either your free creativity or as an opportunity, there is a chance to get the potentials pulled from ab initio calculations. And some of you have already got graduate student helper or postdoc helper and files. So, right? Good. But no matter which projects you do, the protocol is the same code, just different potentials. Okay. this is basically what we will do next Wednesday. Today, those who will come will overview the potentials so that everyone has a potential to work with. Okay, so what have we completed last time? So we did decide that we need to describe rotational motion. Why? Because many things are rotating, and most important thing that does rotate is electron around the nuclei, many electrons around the nuclei. In addition, there are molecules in gas phase that rotate, which gives vibration spectroscopy. So we are going from Cartesian coordinate to first to polar coordinates, and then one can go to spherical coordinates, right? Because distance is either not changing for rigid rudder or slowly changing, and angles that set up the orientation in space are most important. So if our wave function depends on the orientation, on the polar coordinates, then the derivative along the arc length of its along the trajectory can be cast in the form of derivative over the angle, right? So there is no big wonder. And we are coming to the idea that the concept of angular momentum, borrowed from classical mechanics, is something what everyone needs for describing the rotation. Give me a little some signs if the word angular momentum doesn't make you happy. Okay, give me a sign if the word angular momentum makes you happy. There are some indefinite. Give me a sign if you are not ready to immediately give definition of angular momentum. Give me a sign if you are ready to give definition of angular momentum. Okay, I'll try to. So, regular momentum, what is it? It's some quantitative measure of motion, right? If something is moving, then there is a momentum. But it is for regular. If there is a rotational motion, there is another thing that is better measure of motion. So angular momentum is measure of rotational motion. Philosophically. Quantitatively, it is a cross product of the distance between rotating objects and the instantaneous momentum of one of them, if one is heavier and another is lighter. If they are of the same mass, then one selects center of mass and does the reduced distance and reduced mass. But now we are not touching these details. So cross product of the distance from center to moving object times momentum. And by the rules of cross product, it is oriented 90 degrees to both. Right? The quicker the rotation, the larger is angular momentum. Now, if we are speaking only about two-dimensional rotation, then angular momentum has only one component vector, and therefore we can speak of it temporarily only as a scalar, as a projection, because other projections are zero, and it is equal. Its length is equal to simple product of the distance times instantaneous momentum on this trajectory. Okay? And this momentum along the arc length is what we agreed to have as derivative of angle divided by a distance. Right? And here is another distance just from the definition of angular momentum. So they cancel, and therefore we have the operator of z projection of angular momentum as a derivative over the angle, azimuthal angle. If you are happy with this, then most of the remaining things are technical details. So it is very similar to what we did at the very beginning of class and in all of our projects. You have one-dimensional motion, and there is an analog of regular momentum or operator that is derivative over main coordinate. So if we replace this phi symbol to the x symbol, it will be very similar to linear motion. Okay? It is where we, I hope, ended up last time. So what do we do today? What is the ambitious goal? If time allows, I would like to finish with vibrational spectroscopy. It's an ambitious task to squeeze it in 20 minutes. And also overview D and F orbitals, which is also too ambitious. So, what do we do in this class? What is special and different from the rest of the classes that you are attending? It's a record level of being boring. Or what else? Which goal do we set up at each application? What do we do in the projects and when you were looking on the free space, on box, on oscillator?
Predict future?
Yes. So if you want to predict future rotation, how do we achieve this goal? Well, we have some non-standard ways through evolution operator and propagation, numerical propagation, but most typical way to solve time, and we also have the Heisenberg equation of motion, that most typical way is expansion over eigenstates. And predicting the future is needed because we need to predict observables. So for predicting of future, first we may want to find eigenstates. Eigenstates of what?
Of the Hamiltonian?
Yes. So for operator of energy. So if I suddenly forget who am I, where am I, and what I'm doing, and you just remind me, we are in a class and we are describing rotation. Okay, whatever we are describing, first we need Hamiltonian. Second, we need to diagonalize it. So it's simple routine. Like a robot can stand here and diagonalizing Hamiltonian. So what is Hamiltonian for rotational motion? There is no potential, right? Each direction is equivalent. If it is a one like hydrogen atom, one electron around one ion, or diatomic molecule rotating in vacuum, in gas phase. Nothing prevented from rotating freely. So there is no potential energy, there is only kinetic energy. What is the kinetic energy? Regular. Do not look at the screen.
Momentum squared over 2 times the mass.
right? No one objects. So momentum squared over 2 times mass. But it will be not a big sin, not a big. It will be not wrong if we multiply numerator and denominator by anything, by the same factor. So we add r squared to numerator and d in denominator. Okay? No cheating, no lying, just multiplying by the same thing. And then we can rename stuff. We can rename this product r by p as LZ, projection of angular momentum that we did on the previous slide. And we can rename this product of mass times distance as another measure of inertia. So mass, momentum is the measure of motion, mass is measure of inertia. Like if toddler tries to push a big person, it is not very efficient. It needs to fight with inertia. The bigger the mass, bigger the inertia. Same for rotation. If you need to launch rotation of something heavy, it takes more effort. And then the Hamiltonian is recast in different variables. So angular momentum squared over inertia, to inertia. By functional form, it is the same form as before. P squared over 2m. Measure of motion over twice measure of inertia. Here's measure of angular motion squared over measure of inertia. And we may want to recall that we are in the course that exposes us to quantum theory. Therefore, we replace this LZ by this differential operator, take square, and have the Hamiltonian as a second derivative over the angle. Okay? Okay, suppose that I'm suffering from lost memory. Suppose I lost the memory again. Where am I and what I'm doing? Rotational motion, we do have a Hamiltonian. If you do have a Hamiltonian, we need to diagonalize it. Right? Find eigenstates of Hamiltonian. Do I want to do it? Okay, do you want to do it? Probably not, by free will. Me too. But there are some tricks. Well, we cannot do, it's not possible to avoid any activity, but there is a chance to simplify it. So instead of, there will be a bypass. So instead of diagonalizing a Hamiltonian, we will diagonalize something simpler. Now it is time to recall that this course is outstanding. I'm very humble. Compared to regular basic course in physical chemistry or quantum theory. So instead of just going through simple problems, Hamiltonian diagonalized states. Hamiltonian diagonalized states, which is like necessary minimum. In addition to this, we all are exposed to so-called Heisenberg equation of motions, right? And this gives us an opportunity to think out of box. So if, well, Heisenberg equation of motion is like d dt of an observable, it's commutator with Hamiltonian. And if the, it is A, H here. If an observable commutation with Hamiltonian, if the operator of observable commutation with Hamiltonian is 0, then observable doesn't change in time. And there is another consequence. If operator of an observable commutes with Hamiltonian, then eigenstates of this operator and eigenstates of Hamiltonian do coincide, and otherwise. So if we find such operator that which commutation with Hamiltonian is 0, then instead of finding eigenstates of Hamiltonian, we can find eigenstates of this operator, and otherwise. Instead of finding eigenstates of this operator, we can find eigenstates of Hamiltonian. They will be the same. So what you need to know about commutation? Operator commutes with itself, and any power of operator commutes with original operator. So our Hamiltonian here is z projection of angular momentum squared, right? Therefore, it will commute with the operator of this angular momentum projection in the first power. Therefore, instead of finding eigenstates of Hamiltonian, we can find eigenstates of LZ projection. So instead of playing with second derivative, we will play with the first one, which is always easier. So here's our plan. You'll find eigenstates of LZ, and then we will start believing that these eigenstates are also eigenstates of Hamiltonian. So, operator, unknown function. Why do I write it this way? Is everything right here?
Technically.
Yes. I was a little scared because this thing looks very similar to derivative over time, and for the second I thought, like, we are not solving anything time resolved at this moment. But so this is operator. This is not operator here. No. It's not operator. Here is eigenvalue. So LZ with hat acting on wave function gives LZ without hat acting on wave function. And what did we do in the next line? We divide both left and right part on h bar. Z divided by h bar. And we just call LZ divided by h bar equals new variable n. Right? So no one can forbid me to act this way. No violation of mathematical rules, just renaming the variables. So now we do not have any fundamental constants except imaginary unit, and it is relatively simple differential equation that you may want to solve. I know generally no one wants to solve anything, but if we need to solve something, then things as simple as this one. So what will be the answer? It is the only type of equation that we solve again and again in the course. So if a derivative is equal to the function, what will be the function? Do you know the answer? I see smiling faces. What is the answer?
Exponential.
Thank you. Yes. Yes. Then I can skip the whole line. So there is independent variable phi. So we put it on one side. We put the known function on the other side, and we take integrals, and then logarithm equals to independent variable, and then we put this stuff as a power of exponential. So wave function of the two-dimensional rotator will be your favorite thing that looks like plane wave. Right? The only stuff that we do not know what is C capital and we do not know what is M. As soon as we find these coefficients, we will know the eigenfunction of two-dimensional rotation. How do we find C? Yes. So we require that integral over any angle will be equal 1, right? So we take this exponential and its Hermitian conjugate, so it will be just integral from 0 to 2 pi of nothing, of the angle, times c squared. So c squared times 2 pi equals 1, and then we get the c coefficient as 1 over square root of 2 pi. No cheating. Trivial. So wave function, this psi big, this function of phi small, square root of 1 over 2 pi, e I m phi. How do we find m? Were you exposed to solving some such problems in your previous life in this course?
The fact that it's a circle.
Yeah. How does it correlate with particle in the box? The fundamental solution was having the same shape, but then we applied boundary conditions. So in the box, we require that it will be 0 on edges. Right? But there are no edges for circular motion. So there should be something that is equivalent to boundary conditions, or some specific boundary conditions for rotations.
E to the im phi should be equal to the e to the im phi plus 2 pi.
Yes. I don't know what I'm doing here. You guys can teach yourself, and I can just watch it. So psi of phi plus 2 pi should be psi of phi, right? So after making the full cycle, the function should be equal to itself. Like sewing together, having no seam. And if we are thinking in the terms of one-dimensional motion, it is a periodic boundary condition. So it's like a box of the size 2 pi, and departing on one side and reappearing from another side. So it is related to periodic boundary conditions. So how do we practice it? Well, we just plug in this 2 pi phi and phi plus 2 pi into our fundamental form of the solution, right? What is next? Then e to the power phi m phi is cancelled on the left and right, and we have an equation. So 1 is equal to the e I m 2 pi. So we know what is 1, we know what is e, we know what is 2, we know what is pi, we know what is I. So the only thing we do not know is m. It is an equation which we can solve for m, right? I hope I'm not offending you by being slow and trivial. Who is our favorite old buddy?
Euler.
Yes. So if we have exponential with imaginary power. It's sum of real and imaginary part, right? And this real and imaginary part, so cosine of 2 pi m plus I sine 2 pi m equals 1 plus I multiplied by 0. So you can solve either that cosine 2 pi m equals 1 or sine 2 pi m equals 0. Right? And if I'm very tired and lazy, I'll solve equation graphically. So just draw the function oscillating cosine and look for the points when it is equal to 0. When cosine will be equal 1, when the argument is a multiple of 2 pi, right? So if the m is integer, so this equation is fulfilled if m is integer. Argument is multiple of 2 pi. Or we can solve it for this one and get the same answer, that m must be integer, which means 0, 1, or minus 1, 2, or minus 2, right? So here is the wave function for rotations. Are we happy with this function? Not quite, because imaginary things are not easy to visualize. So I'm jumping ahead of time. Okay, 8 minutes more. If we are with these solutions, but we need to plot orbitals, we may identify that several of such orbitals have same energy. I haven't done it yet, but I will in the future. And we can set up linear combinations of these imaginary orbitals in such a way that the results will be real. So if you add exponential moving left and right with to the power plus and minus the same number, you'll get a cosine. If you subtract and divide by I, you'll get sine. And if they are of the same energy, then we will get orbitals which look nicely and are better to visualize. This trick is always done when chemists, and some of us are chemists, plot p, d, and f orbitals. So rotational eigenstates are imaginary, but it is a little crazy to draw imaginary stuff all the time when we do molecules, and we need to concentrate on more important things. So there is a convention of adding and subtracting these imaginary orbitals that will get like px, py, pz orbitals, and like d, z square, or you have seen it or will see it in your favorite inorganic chemistry class. Okay? Makes sense? Good. So it was just a second. I'm not done. Just over here. Here. So it is something you were exposed in the lecture number 3, right? So it is a solution of time-dependent Schrödinger equation for these eigenstates. And initial condition can be taken as with m being integer or non-integer. So if you do it non-integer, you get something ugly. And if you take it integer, then it looks reasonable. What is done here, this thicker line is set up as a 0, and these two lines are sine and cosine, real and imaginary part of wave function. So if it goes a little outward, it is positive. If it goes inward, it is negative. So it's like cosine. Okay? So we agreed, well, I don't know if you agreed, but you were not protesting. We agreed to believe that solutions, eigenstates of LZ operator are also eigenstates of LZ square operator, or the Hamiltonian, for this two-dimensional rotation, right? Excellent. So here is your M, quantum number, and then we can take the matrix element of Hamiltonian in the basis of these functions, which will give us the energy of rotation, right? So if you do it this way, we will find that for this index of rotation, for this quantum state or solution M, the energy will be h bar squared, m squared over 2i, very similar to particle in the box. Okay? So the energy will be square of this parameter. And if we divide it by these factors, we can set up dimensionless energy. So if it goes positive, it grows quadratically. If it goes negatively, it goes quadratically. What do we observe in this picture? So except 0 for each natural number, there is a negative. So there are two numbers that give the same energy. How do you call this situation?
Degenerate states.
Yes. You may have figured out that I'm originally not from this country. And when I just came to the States, I was a postdoc at the University of Oregon, and the secretary of the department I was working at was very nice, gentle, fine lady. And I came to her when I needed to submit an abstract to a conference. They're like, "You're a native speaker, can you just glance through?" And she's not from science at all. I was looking, you know, it's not very polite language.
What?
You know, this word is not a good word. You know, degenerate means some people who are not behaving well. So, those are degenerate. Degenerate. Bad word. Now, I am skipping a month of lecturing and jumping to three-dimensional rotation. So suppose we did operators of angular momentum in polar coordinates. We found eigenstates and we just analyze what they are. So the three-dimensional rotator will depend on two quantum numbers. One is total angular momentum, corresponding to total angular momentum, and another is z projection. And for the z projection, we also can call it m, and the energy will depend on the total length of angular momentum, so total amount of motion. Dependence on the total angular momentum will be very similar to what we had before. It will be almost quadratic. L times L plus 1, which means the parabola is offset to -1/2. But then it is symmetric, so therefore it looks like a beak of a seagull or whatever, some more ugly bird. And then for each value of L, there are several projections. There are several projections of Z angular momentum, except 0. So when there is no rotation at all, there is no degeneracy. If we have first allowed value of total angular momentum, there are 3 degenerate values. If there are next, there are 5 degenerate values. Then 7. Does it recall anything from your experience? Yes, P, D, F, right? So we can set up, we can find out the degeneracy, the energy, and transitions. And when we consider simultaneous excitation of vibrational transition in a molecule and change of rotational state, there will be additional selection rules. And when one summarize dependence of these transitions as incoming frequency, there will be spectrum of rotation, which will depend on selection rules, on these transitions, which follow this thing, and on the occupation. I hope it was slow enough. Many thanks for coming. End of lecture number 38. Everyone is very welcome to the starting of Thanksgiving celebration in the lab. And I plan to share recordings. So it is not tonight is not the most important, but it is preparation to the most important. So if you do not come, please consider to start some preliminary work at home with method for setting up potential and trying to run the wave propagation. Done. If I do not see you anymore today, then have a nice Thanksgiving celebration.